January 5th, 1943, South Pacific waters off Guadalcanal. The morning sun threw long shadows across the deck of the cruiser USS Helena as sailors carried out their duties. Radar operators leaned over their scopes, searching for threats. The war in the Pacific had reached savage intensity, and every man aboard understood that death could arrive at any moment from the sky. Helena had spent the previous night pounding Japanese positions at Munda Airfield on New Georgia. Now, as Task Force 67.2 steamed southward, the crew stayed on high alert. They had learned through bitter experience that Japanese retaliation often came swift and deadly after such strikes. 4 Japanese dive bombers appeared on the horizon, their unmistakable silhouettes clear. IED-3A aircraft, codenamed Valves by Allied forces. They were older models, slower than the newer D-4Y types, but in the hands of seasoned pilots, their accuracy made them lethal. The alarm rang through the ship. Battle stations. Every gun crew scrambled into position. The Japanese planes dove toward the American task force, their bombs finding a mark on HMNZS Achilles before they began to withdraw. What happened next would alter warfare forever. As the Japanese bombers climbed away, believing they had escaped the reach of American guns, Helena's 5-inch 38 caliber batteries opened fire. Not the frenzied salvo of hundreds of rounds naval doctrine prescribed, but only a handful of shells. The gun crews watched as the projectiles streaked toward the distant aircraft, now more than 4 miles away. Then something remarkable occurred. The shells detonated near the planes without striking them directly. One bomber burst into flame and rolled into the sea. Another followed seconds later. The gun crews stared, stunned. They had witnessed what seemed impossible by existing naval standards. Enemy aircraft downed at extreme range without direct hits. The shells had detonated automatically as they neared their targets. No elaborate timing calculations, no guessing at altitude and speed, no frantic fuse adjustments. The weapons simply sensed proximity and exploded at the precise moment. Commander W.S. Parsons, who recorded the engagement, noted the extraordinary nature of the event. These were not lucky shots. They were precision kills delivered by a munition that detected its distance to the target and detonated at exactly the right instant to inflict maximum damage. What those sailors had used was a secret so closely guarded it ranked just behind the atomic bomb. Project in security classification, a technology so revolutionary that commanders feared its capture more than nearly any other. A device that would prove several times more effective than conventional shells. Yet despite its enormous potential to save American lives, top military authorities would decline to authorize its broad use for almost 2 years. This is the story of the proximity fuse. The weapon the Navy initially kept to itself, the innovation Pentagon officials considered too hazardous to deploy on land, and the secret that would ultimately help win World War II. To understand why leaders restricted such a powerful armament, we must first see what made it so extraordinary. Before 1943, shooting down an airplane with anti-aircraft artillery was an exercise in mathematical futility. The problem was simple to state, but fiendishly difficult to solve. The sky is vast. Aircraft are comparatively small. They move at high speeds in 3 dimensions. Artillery shells, once launched, follow fixed ballistic trajectories that cannot be steered. Traditional anti-aircraft guns relied on 2 types of fuses, each with crippling limits. Contact fuses detonated only upon impact, demanding a direct hit on a fast-moving object at distances often measured in miles. A vanishingly unlikely outcome. Time fuses exploded at a preset moment after firing. Crews had to predict the exact instant when the shell would be closest to the aircraft, accounting for altitude, speed, heading, climb or descent rate, wind, and the shell's own trajectory. Any error, even a fraction of a second, meant the shell blew up harmlessly in empty air while the enemy plane sailed on. The statistics from the early war years were grim. At the outset of the European War, it required roughly 20,000 rounds of anti-aircraft ammunition to down a single enemy aircraft. Some figures from the Norwegian campaign and the Battle of Britain put the number as high as 100,000 rounds per kill. Even optimistic estimates by experienced crews suggested at least 2,500 rounds were necessary to destroy one plane. Naval vessels and shore batteries burned through vast quantities of ammunition with little to show for it. Ships returned to port with magazines emptied and enemy aircraft still dominant overhead. The human cost of this inefficiency was paid in blood and wreckage. Japanese dive bombers and torpedo planes devastated Allied naval forces in the Pacific. At Pearl Harbor, at the Coral Sea, at Midway, sailors died because anti-aircraft guns could not reliably stop attacking aircraft. German planes menaced Atlantic convoys, sinking merchantmen carrying vital supplies to Britain and the Soviet Union. Allied ships endured near-constant aerial assault, while defensive weapons were, in practical effect, barely more useful than rifles. Sailors perished in burning ships. Supply vessels carrying food, fuel, and ammunition sank before reaching port. The fate of entire campaigns hung on the Allies' inability to defend effectively against determined air attack. Scientists and planners across the belligerent nations recognized the need for a superior solution. The idea of a proximity fuse, a shell that could sense its target and detonate at the optimal distance for maximum effect, had been debated in CCTWA journals and laboratories for decades. The British had started preliminary work in 1939, driven by the rising threat of German air power. The Germans themselves launched numerous proximity fuse programs, with some sources noting dozens of separate efforts. The Japanese experimented with acoustic and magnetic detection systems. Everyone appreciated the weapon's transformative promise. But recognizing promise and producing a usable device were wholly different challenges. The technical hurdles seemed insurmountable with 1940s technology. Every major power tried and failed in various degrees. German programs were particularly active, initiating many lines of research by 1940, including acoustic detectors and radio-based approaches. Yet in 1940, Hitler ordered research funneled into projects that could reach production within 6 months. A decision born of overconfidence after early victories that proved catastrophic. When German work resumed in 1944 as the situation worsened, it was too late. Some German firms had even test-fired prototypes by late 1944, but their facilities were overrun before production began. Not a single German proximity fuse saw operational service during the war. While the Americans manufactured millions, the Japanese Naval Technical Research Institute understood the concept, but lacked the industrial base for miniaturized electronics. Japanese vacuum tubes were larger, less reliable, and ill-suited to survive firing stresses. Their best efforts produced laboratory curiosities with no path to mass manufacture. A proximity fuse had to contain a miniature radar system capable of detecting aircraft and computing range in real time, packaged inside an artillery shell only 5 inches in diameter. The components had to survive acceleration forces of tens of thousands of times gravity when fired from a naval gun. The shell spun at tens of thousands of revolutions per minute in flight, producing enormous centrifugal forces. The device would need to function flawlessly in rain, snow, tropical humidity, Arctic cold, and the chaos of combat conditions. And it would need to be cheap enough to manufacture by the millions. Most experts considered it impossible with existing technology. Vacuum tubes, the basic building blocks of all electronic circuits in that era, were delicate glass containers that shattered under far less stress than artillery shells injured. Even reinforced tubes failed when subjected to a tiny fraction of the forces involved in gun firing. Batteries powerful enough to run a radar system were far too large to fit in a shell nose. The radar antenna would need to be impossibly small yet still functional. The safety mechanisms required to prevent premature detonation would need to work perfectly every single time without exception. One failure could kill the entire gun crew firing the weapon. And all of this technology would need to be crammed into a space smaller than a coffee can, then fired from a gun with explosive force. The British shared their early research with American scientists in September 1940 through the Tizard mission, a desperate intelligence exchange undertaken as Britain stood alone against Nazi Germany. Sir Henry Tizard arrived in Washington carrying a black metal deed box that contained many of Britain's most closely guarded military secrets. Among the documents were preliminary designs for a proximity fuse, theoretical calculations, and reports on failed experiments. But British scientists admitted they lacked both the industrial capacity and the specialized knowledge in miniaturized electronics to turn theory into mass-reduced reality. Britain's factories were already stretched beyond capacity, producing conventional weapons. The challenge of developing the proximity fuse fell to American researchers. The National Defense Research Committee, which had been formed on June 27, 1940, assigned the project to Dr. Merle Tuvey at the Applied Physics Laboratory of Johns Hopkins University. The choice was inspired. Tuvey was a physicist who had spent years studying the ionosphere using radio waves, giving him exactly the background needed for this challenge. He assembled a team of physicists, engineers, and inventors from universities and private industry. They worked under conditions of absolute secrecy that rivaled the Manhattan Project itself. The project received security classifications second only to the atomic bomb. Workers in the factories often had no idea what they were building. Components were manufactured separately with deliberately misleading names. The fuse was given the intentionally vague codename variable time, abbreviated VT, to hide its true nature even from most military personnel who would handle it. Section T, as Tuvey's group became known, faced one technical crisis after another. Each problem solved seemed to reveal two new challenges. The team initially consisted of just 4 scientists in August 1940, but would eventually grow to nearly 1,000 researchers and support staff. They worked in converted buildings at Johns Hopkins and the Department of Terrestrial Magnetism at the Carnegie Institution. Security was so tight that different teams working on components often had no idea how their work related to other parts of the project. Standard vacuum tubes shattered instantly under the massive acceleration forces of gun firing. Early tests were disasters. In one documented test, engineers fired a standard radio tube from a gun and recovered only glass powder and twisted wire. Even tubes marketed as ruggedized and used in oil drilling equipment failed catastrophically. The acceleration was so violent that glass would flow like liquid. Internal elements would telescope into each other, and delicate wire grids would collapse instantly. The breakthrough came through partnership with private industry. Sylvania Electric Products, working with Section T engineers, developed special miniaturized tubes with reinforced glass, multiple support structures, and shock-resistant internal components. These tubes were unlike anything previously manufactured. They started with hearing aid tubes, the smallest available, and modified them extensively. Additional glass supports were added at critical stress points. Lead wires were shortened to just 3/208 of an inch to reduce flexing. Special tungsten alloy filaments replaced standard materials. The tubes were filled with special gas mixtures at precise pressures to prevent electrical arcing under stress. But even these improved tubes failed repeatedly in early tests. In one particularly frustrating series of experiments, in late 1941, 900 consecutive tubes were destroyed without a single success. Engineers tried everything imaginable. They embedded the tubes in wax, finding it melted from heat. They tried oil which leaked. They experimented with rubber compounds that deteriorated. They tested various plastics that cracked under stress. One engineer suggested suspending the tubes in mercury, which was too heavy. Another proposed using human blood plasma as a cushioning medium, which was tested but proved impractical. The solution came from an unexpected source, Dr. James Van Allen, who would later discover the Van Allen radiation belts, was then a young physicist. On the team, He suggested using a wax and oil combination in precise ratios with the tubes mounted at specific angles to distribute stress. After thousands of configurations, they found that tubes mounted at 30° to the shell's axis, cushioned in a mixture of sarin wax and transformer oil, could survive about 70% of test firings. This was deemed acceptable for wartime production. The battery problem seemed equally insurmountable with conventional technology. Standard batteries were far too large and could not activate instantly. The solution, when it came, was ingenious and counterintuitive. Engineers created a tiny glass ampule containing liquid electrolyte. The ampule sat inert until the shell was fired. When the gun fired, the massive acceleration shattered the glass, and centrifugal force from the shell's spin drove the liquid outward to contact carefully positioned metal plates. This initiated a chemical reaction that generated electrical current. The battery literally activated itself through the very forces that threatened to destroy it. It was elegant engineering, using the problem as its own solution. The radar system required innovations that pushed the boundaries of electronics technology. Traditional radar systems were enormous installations weighing tons. The proximity fuse radar had to fit in a space the size of an ice cream cone. The transmitter and receiver had to share a single tiny antenna no larger than a pencil. The circuitry needed to distinguish between the radio signal it was transmitting and the much weaker reflection bouncing back from the target. Section T engineers developed an ingenious autodyne detector circuit that could sense minute changes in signal strength as the shell approached its target. When the reflected signal exceeded a specific threshold, indicating the target was within lethal range of the shell's fragments, the firing circuit would trigger the detonation. But detecting proximity alone was not enough. The fuse had to be smart enough to avoid false triggers. A shell fired over water could not be triggered by reflections from ocean waves. A shell fired in rain could not mistake water droplets for aircraft. A shell passing near friendly aircraft had to distinguish friend from foe. Though this proved impossible and led to strict usage protocols, engineers added sophisticated wave suppression circuits that ignored long-duration signals from stationary surfaces while remaining sensitive to the characteristic reflections from moving aircraft. They built in time delays so the fuse could not arm until the shell had traveled safely away from the firing ship. The arming sequence was complex, requiring multiple conditions to be met in precise order. Safety mechanisms had to be redundant and absolutely foolproof. The fuse remained completely inert until fired. The battery contained no active chemicals until the ampule shattered. The arming circuit required both battery activation and a minimum time of flight, typically 700 YD from the gun. The radio transmitter powered up only after the shell had spun up to the correct rotational speed using a centrifugal switch. Multiple independent systems had to align perfectly before the weapon became dangerous. One failure in any safety circuit meant a dud shell that fell harmlessly into the ocean, protecting both the gun crew and the secrets inside the fuse. The first successful test came on August 12, 1942, when the newly commissioned light cruiser USS Cleveland conducted live fire tests in the Chesapeake Bay during its shakedown cruise. Radio-controlled drone aircraft served as targets. The results exceeded all expectations. Gunners shot down 3 drones with just 4 bursts on the first day. The drone aircraft were small, fast, and maneuvering. Yet, the proximity-fused shells destroyed them with ease. The test was so successful that the Navy canceled the planned second day of testing and immediately ordered mass production. By January 1942, after 18 months of intensive work involving thousands of experiments, the team had produced fuses that exceeded 50% reliability in test firings. By peacetime standards, this would have been unacceptable. But with American forces suffering severe losses to enemy air attack, 50% reliability of a revolutionary weapon was deemed acceptable. Production of the Mark 32 VT fuse began in November 1942. The first operational fuses reached Pearl Harbor that same month, traveling under heavy guard in sealed containers. The Pacific Fleet received 4,500 fuses by the end of the year, distributed only to select cruisers and battleships. The Navy's security protocols surrounding the new weapon were extraordinary and unprecedented. VT-fused shells could only be fired over deep water where the depth exceeded 100 fathoms. Any dud that failed to detonate would sink to the ocean floor, taking its secrets beyond enemy reach. Ships received strict orders never to use the fuses, where they might fall on land or in shallow water. The penalty for violating these orders was severe, including potential court-martial. Commanding officers had to personally approve each use. The fuses were stored in special magazines under Marine Guard. The technology was simply too valuable to risk any possibility of capture. In early January 1943, Helena put the new fuses to their first real combat test off Guadalcanal. The results exceeded all expectations. The ship's gunners fired only 22 rounds and achieved 2 confirmed kills at ranges previously thought impossible. A gunnery report filed after the engagement stated the value of the Mark 32 fused projectile cannot be too highly stressed. The Bureau of Ordnance had been waiting anxiously for exactly this kind of combat confirmation. Production ramped up immediately, with contracts expanding from $60 million to over $200 million within months. Throughout 1943, VT-fused ammunition proved itself in battle after battle across the Pacific. Ships firing these shells downed enemy aircraft with unprecedented efficiency. During 1943, naval guns fired 36,370 anti-aircraft rounds. Although only 25% used proximity fuses, these shells accounted for 51% of all aircraft destroyed. The mathematics were stunning and undeniable. Time-fused shells required an average of 508 rounds to destroy one aircraft. Proximity-fused shells required only 155 rounds per kill. The new technology was more than 3 times as effective as conventional ammunition. The lethal fragment area comparison told an even more dramatic story. A 5-in time-fused shell, if it exploded at exactly the right moment and position, could spray lethal fragments across roughly 60 square ft. This required perfect timing and positioning, rarely achieved in combat. A proximity-fused shell created a lethal kill zone of 3,000 square ft, guaranteed to detonate at the optimal distance from the target. The effective target area had become 50 times larger from the perspective of the explosive. An aircraft that would have flown safely past a time-fused explosion now flew directly into a cloud of deadly shrapnel. Night engagements revealed another crucial advantage. Time fuses required accurate range and altitude data to set the detonation time. At night, without visual confirmation, these calculations became even more difficult and unreliable. Radar could track aircraft position, but could not always provide the precision needed for time fuse settings. Proximity fuses eliminated this problem entirely. The shell found its own target regardless of visibility conditions. Night kill ratios increased by 370% when ships used VT ammunition. Japanese pilots, who had previously used darkness as protection, suddenly found themselves just as vulnerable as in daylight. Admiral William Holtze, commanding naval forces in the South Pacific, recognized the strategic implications immediately. Japanese torpedo planes had been making devastating nighttime attacks on American ships throughout 1942. The darkness protected the attackers and limited defensive fire to wild barges aimed at engine noise. With proximity fuses and radar-controlled gun directors, this advantage evaporated overnight. Ships could engage aircraft effectively in pitch darkness at extended ranges. Japanese aircrew losses mounted dramatically. The tactics that had terrorized the fleet became suicide missions. By late 1943, Japanese naval aviation was suffering unsustainable losses, partly due to the proximity fuse's effectiveness. Yet even as Navy ships reaped these benefits, Army commanders in Europe fought with one hand tied behind their backs. They knew the proximity fuse existed, Intelligence reports and liaison officers had informed them of the Navy's success. They knew it could save their soldiers' lives. General Dwight Eisenhower, Supreme Allied Commander in Europe, had seen the statistics, and they had been refused permission to use it. The Pentagon's logic was based on legitimate security concerns that seemed reasonable at the time. Every artillery shell fired over land carried an inherent risk. Some shells would inevitably malfunction and fail to detonate. Some would fall in contested territory where German forces might recover them. If the Germans captured even one intact fuse and successfully reverse-engineered it, the consequences could be catastrophic. German engineers might develop their own proximity, fuses for the anti-aircraft guns defending the Reich. The American and British strategic bombing campaign depended on being able to reach targets deep in Germany. If German flak batteries suddenly became 3 to 4 times more effective, bomber losses would become unsustainable. The air war over Europe would be lost. Intelligence reports suggested German science was fully capable of understanding and replicating the technology if given a working example. German electronics firms like Telefunken and Siemens had sophisticated research facilities. German scientists had already experimented with various proximity fuse designs, though none had reached production. There was also fear of German jamming technology. If enemy scientists figured out the radio frequency used by the fuses, they might develop electronic countermeasures. False signals could trigger premature detonation or prevent the fuses from working at all. The advantage would be neutralized and the secret revealed for nothing. Better to maintain strict operational security than risk the scenarios. So the Pentagon maintained its embargo through most of 1944. The Navy could use proximity fuses over deep water, where duds would sink beyond recovery. But the Army could not use them in Europe, where every shell mattered. This decision had devastating consequences. Measured in American blood, time-fused artillery in the European theater continued to require thousands of rounds to achieve meaningful results. German formations moved with relative impunity because Allied artillery lacked the precision to stop them consistently. American soldiers died, while a weapon that could save them sat in warehouses waiting for authorization that might never come. Army commanders grew increasingly frustrated as 1944 progressed. They were fighting the Wehrmacht with inferior technology, while a war-winning weapon remained restricted. General Dwight Eisenhower understood exactly what the proximity fuse could mean for his troops. He had reviewed the Navy's combat data showing threefold improvements in effectiveness. He knew that American soldiers were dying unnecessarily because of what he considered overly cautious security policy. And he was not a man who accepted unnecessary casualties quietly. The military situation grew increasingly desperate by late 1944, despite successful D-Day landings. In June and the liberation of France, German forces were far from defeated. They had stabilized their lines along the German border and were preparing a massive counteroffensive. Unknown to Allied intelligence, Hitler had assembled a strike force of 250,000 soldiers, nearly 500 tanks, and 2,000 artillery pieces in the Ardennes forest. The German plan, surnamed Operation Watch on the Rhine, aimed to split the Allied armies, recapture the vital port of Antwerp, and force the Western Allies to negotiate a separate peace. On December 16, 1944, at 5:30 in the morning, Germany launched its surprise offensive. The attack began with a massive 90-minute artillery barrage that stunned American forces. 250,000 German soldiers, supported by the secretly assembled tank forces, smashed into American lines along an 80-mile front. The assault hit a thinly defended sector held by inexperienced and recuperating divisions. The 106th Infantry Division had just arrived from the United States. The 28th Infantry Division was recovering from severe losses in the Hürtgen Forest. German armored spearheads led by elite SS Panzer divisions penetrated. deep into Allied territory. The weather was terrible with low clouds and snow preventing Allied air support. American forces reeled, backward in confusion and near panic. The Battle of the Bulge had begun. American artillery fought desperately to slow the German advance, but time-fused shells proved woefully inadequate against infantry advancing across snow-covered open ground. Artillery observers struggled to provide accurate range data in the confusion. Too many shells buried themselves in the soft earth and snow, detonating harmlessly underground. Too many German soldiers survived artillery barges that should have destroyed entire units. German infantry advanced with confidence, knowing that American artillery, while dangerous, was not the precision killer it could have been. 3 days into the German offensive, with American forces in crisis, Eisenhower had seen enough. He sent an urgent message to the Pentagon through General George Marshall, Army Chief of Staff. Eisenhower demanded immediate authorization to use proximity fuses in ground artillery. He argued that this strategic situation overrode security concerns. If the Germans broke through to Antwerp and split the Allied armies, the entire campaign would collapse. The war would be prolonged by months or years. The risk of captured fuses, terrible as it might be, was less than the risk of losing the campaign. The Pentagon relented with remarkable speed. On December 21, 1944, all restrictions on proximity fuse use were removed. Within hours, 200,000 shells with VT fuses, code-named POSIT, to maintain some operational security, were released from depots and rushed to the front lines. Artillery battalions received hurried briefings on the new ammunition. Most gun crews loaded the shells with no clear understanding of how they worked, only promises that they were far more effective than anything previously fired. The results were immediate and devastating. American artillery that had been marginally effective against German infantry suddenly became a precision killing machine. Shells exploded perfectly at treetop height, without requiring any time fuse calculations. Every round detonated at the optimal height to spray fragments across the maximum area. German soldiers advancing across snow-covered fields found themselves in kill zones with no protection. Units that had felt relatively safe from time-fused artillery because heavy clouds prevented accurate observation now died in droves. The bad weather that was supposed to protect them made no difference to proximity fuses that needed no external targeting data. General George Patton commanded the Third Army as it drove north to relieve surrounded American forces at Bastonia. His artillery battalions received proximity fused ammunition on December 22nd. The very next day, they put it to devastating use. Near Eichenach in Luxembourg, a battalion of German infantry attempted to cross the Sauer River to reinforce their offensive. Patton's artillery caught them in the open. The new shells with the funny fuses, as Patton called them in his diary, killed 702 enemy soldiers by actual body count. The German battalion ceased to exist as an effective fighting force. Patton wrote a letter to Major General Levin Campbell, Jr., Chief of Army Ordnance, expressing his amazement at the new weapon. "The new shell with the funny fuse is devastating," he wrote. "We caught a German battalion which was trying to get across the Sauer River with a battalion concentration and killed by actual count 7,002. I think that when all armies get this shell, we will have to devise some new method of warfare. We will have to devise some new method of warfare. I am glad that you all thought of it first." This was not hyperbole from a man known for dramatic statements. This was sober professional assessment from one of America's most experienced combat commanders. German soldiers captured after proximity fused artillery strikes described the attacks in terms of shock and complete helplessness. One prisoner from the 12th SS Panzer Division stated there was simply no defense against the new American shells. They exploded overhead with no warning, raining fragments straight down. Men in foxholes and trenches, previously protected from artillery that exploded on the ground, now died as steel fragments came from above. German commanders had no tactical response. They could not adapt to a weapon that eliminated the traditional defensive positions that had protected infantry since World War I. The 8th Infantry Division caught a German patrol in the Hürken Forest using a time-on-target barrage with proximity-fused shells. All 96 Germans were found dead. The patrol completely annihilated without a single survivor. Such devastating results multiplied across the front as American artillery battalions learned to employ the new ammunition effectively. German offensive momentum ground to a halt by December 25th. The counteroffensive that was supposed to split the Allied armies and win breathing space for Germany instead became a catastrophic defeat that destroyed the last German strategic reserves. Allied anti-aircraft batteries also benefited dramatically from the lifted restrictions. German aircraft, making desperate close support attacks, suddenly faced the same lethal technology that had ravaged Japanese air power in the Pacific. German planes fell to proximity-fused anti-aircraft fire during the Battle of the Bulge period. The Luftwaffe's last major offensive effort collapsed under losses it could not sustain. Air superiority, always tenuous for Germany by late 1944, became completely unattainable. The port of Antwerp demonstrated another critical application of proximity-fused technology. The Belgian port was absolutely essential for Allied logistics, handling more supplies than all other ports combined. Its capture intact in September 1944 had been a major strategic victory. But the Germans responded with concentrated V-1 flying bomb attacks beginning in October. These primitive cruise missiles, essentially pilotless aircraft powered by pulse jet engines, flew at nearly 400 mph at altitudes between 2,000 and 3,000 ft. Their speed and low altitude made interception extremely difficult with conventional anti-aircraft weapons. When proximity fuses became available for the anti-aircraft batteries defending Antwerp, the equation changed overnight. Modified fuses designed specifically for low-altitude, high-speed targets turned the defenses into a nearly impenetrable barrier. In one 24-hour period, 48 of the first 75 V-1s approaching Antwerp were destroyed by proximity-fused anti-aircraft fire. The success rate climbed to nearly 80% as gun crews gained experience with the new ammunition. The vital supply port remained operational throughout the winter of 1944, enabling Allied forces to maintain their advance into Germany. Without proximity fuses, Antwerp would likely have been rendered unusable, potentially stalling the Allied offensive for months. The British capital also benefited enormously from American proximity-fused technology. London had suffered terribly under V-1 attacks beginning in June 1944. The flying bombs caused extensive damage and civilian casualties, threatening to break civilian morale. British anti-aircraft defenses initially struggled to intercept them effectively, destroying less than 20%. American proximity fuses rushed to Britain and integrated into British anti-aircraft guns, transformed the defensive capability almost overnight. By the end of August 1944, anti-aircraft batteries equipped with proximity fuses were destroying 79% of all incoming V-1s. During 1 week in August, guns using proximity fuses destroyed 82% of V-1s targeted. London was saved from a weapon that might have forced consideration of evacuation plans. In the Pacific theater, the proximity fuse's importance grew even greater as Japanese tactics evolved into organized kamikaze attacks. By October 1944, Japan had lost most of its experienced pilots at the Battle of the Philippine Sea and other engagements. The Marana's turkey shoot in June had cost Japan over 600 aircraft and most of their remaining trained aviators. Conventional attacks by poorly trained replacement. Pilots stood little chance against American fighter cover and ship defenses with loss rates exceeding 80%. Vice Admiral Takejiro Onishi, commander of the 1st Air Fleet in the Philippines, formerly organized the special attack units known as Kamikazeon, October 19, 1944. The 1st unit, the Shimpu Special Attack Corps consisted of 24 volunteer pilots flying bomb-laden Zero fighters. Onishi told the pilots they were already gods without earthly desires. Their mission was not to return. These units used aircraft as guided missiles piloted by men who accepted death as the starting point of their mission. The first organized kamikaze attack occurred on October 25th during the Battle of Lee Gulf. Lieutenant Yukio Ki led fivers against American escort carriers off Samar. One kamikaze crashed into the escort carrier USS St. Lo, detonating in the hangar deck among fueled aircraft. The ship exploded and sank within 30 minutes with the loss of 143 crew members. Other kamikazes damaged the carriers Santiswani, Kitkun Bay, and Kinanan Bay. The psychological impact on American sailors was profound and immediate. This was not warfare as they understood it. Naval commanders immediately recognized that proximity fuses would be critical against this new threat. Emergency orders went out to equip every ship possible with VT ammunition. Production priorities shifted. Ships heading to the Pacific received priority allocation of proximity-fused shells. Gun crews received special training on engaging kamikaze aircraft, emphasizing sustained fire at maximum range, using proximity fuses to create a wall of exploding shells. The kamikaze threat was both terrifying and initially effective. Pilots who accepted death at the outset could not be deterred by defensive fire. They would fly through flak and fighters, absorbing damage that would force conventional attackers to turn away. They required only enough control to reach their target in the final seconds. At Lady Gulf in October 1944, kamikazes sank the escort carrier USS St. Lo and damaged numerous other vessels. The psychological impact on American sailors was profound. Proximity fuses proved uniquely effective against kamikazes for reasons that became clear through combat analysis. The suicidal nature of the attacks meant Japanese pilots flew predictable straight-line trajectories directly toward their targets. No evasive maneuvers, no complex approach patterns, no pulling away at the last second. This predictability played directly to the proximity fuse's strengths. 5-in guns firing VT ammunition required only 310 rounds per kill against kamikaze attackers, compared to 624 rounds per kill against conventional attacks. The simpler trajectory gave the fuses more opportunities to detect and destroy the incoming aircraft. The Battle of Okinawa, from April to June 1945, became the ultimate test. Ofanti aircraft defenses against mass kamikaze attacks. Japan threw everything remaining at the Allied fleet, supporting the invasion. Nearly 2,000 kamikaze sorties attacked American ships over 3 months of desperate fighting. The Japanese called these mass attacks kikusui, meaning floating chrysanthemum, and launched 10 major waves. On April 6th alone, 355 kamikaze aircraft attacked the fleet. The scale was unprecedented and initially overwhelming. American naval forces suffered the highest casualties of any Pacific campaign. 26 ships were sunk and 164 damaged. Nearly 5,000 sailors died and another 5,000 were wounded. But without proximity fuses, the losses would have been catastrophic rather than merely severe. Nearly 2 to 3 of all VT fuses expended during the entire war were used in just 7 and 12 months of 1945, most of them in the waters around Okinawa. Those fuses shot down over 200 Japanese aircraft that otherwise might have crashed into American ships. The invasion succeeded, but at a cost that influenced American planning for the invasion of Japan itself. Postwar analysis by the Operations Research Group concluded definitively that proximity-fused shells were 3 to 4 times as effective as time-fused ammunition in anti-aircraft roles. Some specific scenarios showed even greater advantages. 5-in naval guns firing conventional time-fused ammunition required approximately 2,000 rounds to destroy one aircraft in typical combat conditions. The same guns using proximity fuses required between 300 and 600 rounds depending on the tactical situation. Against kamikaze attacks specifically, the advantage was even more pronounced, with some engagements showing 5 to 10 times greater effectiveness. The proximity fuse provided a psychological advantage that is harder to quantify, but no less real. Japanese pilots facing intense proximity-fused anti-aircraft fire knew that even near misses could be lethal. The sky filled with air burst explosions that seemed to track their movements with uncanny accuracy. German soldiers in Europe learned to fear American artillery in ways they had not previously. The shells found targets that conventional ammunition missed. They exploded at exactly the right height, regardless of weather or terrain. There was no safe place, no reliable protection, no tactical counter. The proximity fuse also validated a revolutionary model of military research and development that would shape American defense policy throughout the Cold War and beyond. The project demonstrated conclusively that civilian scientists, given adequate resources and clear objectives, could solve seemingly impossible technical challenges. The collaboration between academic researchers at Johns Hopkins, industrial manufacturers like Crossley and Sylvania, and military planners had produced a war-winning weapon in under 3 years from initial concept to mass production. The industrial achievement was as impressive as the technical innovation. The proximity fuse program represents one of the greatest production miracles of World War II, comparable to the B-29 bomber or Liberty ship programs. At the program's peak in early 1945, over 110 factories operated by 87 different companies participated in proximity fuse production. This vast network employed over 100,000 workers, most of whom had no idea what they were building. The production story began modestly. In August 1942, Crossley Corporation in Cincinnati received the first production contract. Powell Crossley Jr., who had made his fortune in radios and refrigerators, converted his entire factory to fuse production within weeks. Security was extraordinary. Workers passed through multiple checkpoints. They wore color-coded badges that restricted access to specific areas. Mail was censored. Phone calls were monitored. Workers were forbidden to discuss their jobs, even with family members. Many thought they were making improved radio tubes for military radios. Crossley's plant became a model for mass production efficiency. The assembly line was divided into stages, with workers trained on single operations they repeated thousands of times. One station wound tiny coils, another solid connections with microscopic precision. Quality control inspectors checked every 10th unit. By December 1942, Crossley was producing 500 units daily. By December 1943, production reached 3,000 units daily. At the program's peak in April 1945, Crossley alone was producing 1,600 fuses every 24 hours. RCA entered production in September 1942, converting a facility in Bloomington, Indiana. Their expertise in radio manufacturing proved invaluable. RCA engineers developed improved assembly techniques that reduced production time by 30%. Eastman Kodak's contribution went beyond assembly. Their expertise in precision optics and chemistry helped solve problems with the photoelectric cells used in some fuse variants. They also developed improved plastic components that could withstand temperature extremes. General Electric operated multiple facilities. Their plant in Schenectady, New York, assembled complete fuses, but their most important contribution came from a converted factory in Cleveland that had previously manufactured Christmas tree lights. This facility produced the tiny tungsten filaments used in the vacuum tubes, working to tolerances measured in thousandth of an inch. A single imperfection invisible to the naked eye could cause fuse failure. Sylvania Electric Products became the backbone of tube production. Their plant in Ipswich, Massachusetts, employed 10,000 workers in 3 shifts, operating continuously except for Christmas Day. The plant consumed enough electricity to power a small city. Special air filtration systems removed dust particles that could contaminate tubes. Workers wore special clothing to prevent static electricity. The plant produced 95% of all proximity fuse tubes, manufacturing approximately 1 million tubes every 212 days at peak production. By war's end, Sylvania's Ipswich facility alone had produced 32 complete fuses, more than any other single location. Major corporations worked alongside dozens of smaller specialized firms. McQuay Norris Manufacturing Company in St. Louis produced metal components. Zenith Radio Corporation in Chicago assembled electronic modules. Wurlitzer, famous for organs and jukeboxes, manufactured precision timing mechanisms. Even Lionel Corporation, known for toy trains, produced specialized components. Each company brought unique expertise that contributed to solving production challenges. By war's end, American industry had produced 22 million proximity fuses at a total cost exceeding $1 billion in 1940s currency. The cost per fuse dropped dramatically through mass production efficiency. Early hand-assembled fuses cost $7.32 each, making them more expensive than many automobiles. By 1945, assembly line production and manufacturing improvements had reduced the unit price to $18. This 40-fold cost reduction made the weapons economically viable for widespread use. Even at $18 each, proximity-fused shells were cost-effective when their dramatically improved kill rates were considered. Quality control was obsessive throughout the program. Every batch of fuses underwent rigorous testing at multiple stages. The National Bureau of Standards operated special testing facilities. Fuses were subjected to temperature extremes from 65 to plus 160 degree F. They endured humidity chambers, salt spray tests, vibration tables, and centrifuges that simulated firing conditions. Random samples from each production lot were actually fired to verify functionality. The failure rate had to remain below strict thresholds. Any batch showing problems triggered investigation of the entire manufacturing run. This attention to quality ensured that fuses performed reliably in combat from the Arctic to the tropics. The secrecy surrounding the proximity fuse held remarkably well throughout the war. Despite millions of fuses being fired in combat, the Axis powers never successfully reverse-engineered the technology or developed effective countermeasures. German engineers captured some dud shells in late 1944, but could not believe the fuses actually worked as advertised. The idea of functional radio equipment surviving inside an artillery shell seemed so improbable that they assumed the captured examples were elaborate deceptions or failures. They spent valuable resources developing countermeasures against fusing, methods the Americans were not even employing. The Japanese faced similar, though even more overwhelming, technical barriers. They recovered several dud proximity-fused shells during Pacific campaigns, especially from naval bombardments that overshot and landed ashore despite strict regulations. Japanese engineers understood the underlying concept, but their electronics industry lacked the ability to reproduce the extreme level of miniaturization required. By 1943, the technological gap between American and Japanese industry had widened so dramatically that even with captured examples, Japan could not manufacture equivalent weapons in any meaningful number before the war's end. Secretary of the Navy James Forrestal, reflecting on the proximity fuse's contribution to victory, stated that it helped blaze the trail to Japan. General Eisenhower, in his memoirs, wrote that if the Germans had perfected and deployed proximity fuses 6 months earlier than the Allies, the invasion of Europe would have been exceedingly difficult, perhaps impossible. These were not offhand remarks. They were strategic evaluations from the highest echelons of command, from men who fully grasped how thin the line between victory and defeat truly was. Yet for nearly 2 years, Army field commanders were denied access to this revolutionary weapon due to institutional caution that, while understandable, ultimately proved excessive. The Pentagon's security fears were justified. The danger of enemy, reverse engineering was real. But the decision to maintain the ban while American troops fought and died with inferior munitions reflected a lapse in strategic judgment. It prioritized hypothetical future risks over immediate battlefield survival. Only when the situation grew. Desperate during the Battle of the Bulge did top leadership finally approve what should have been authorized long before. Laihibi. Proximity fuse represented far more than a simple improvement in weaponry. It symbolized a turning point in how modern militaries approach technology, proving that electronics and automation could dramatically enhance traditional arms. It showed that small technological breakthroughs, properly utilized, could decide the fate of entire campaigns. Most importantly, it revealed that true innovation required not only brilliant science, but also vast industrial capacity and the institutional will to embrace change despite risk. The sailors aboard the USS Helena, who fired those first combat rounds in January 1943, could not have realized they were ushering in a new era of warfare. They only knew their shells were striking targets once thought unreachable. But their superiors, the officers, admirals, and generals who directed those forces, recognized that something fundamental had shifted. War had entered a new phase in which technological mastery mattered as much as bravery and manpower. In less than 3 years, American scientists and manufacturers had conceived a weapon that redefined combat, produced it by the millions, fielded it across 2 hemispheres, and used it to help secure victory in the greatest conflict in human history. The device the Navy once hoarded became the weapon that helped save the Allied cause at its most perilous hour. The innovation Pentagon officials once deemed too dangerous to deploy became indispensable to success. That transformation, from forbidden to essential, stands as a testament to what human ingenuity can achieve. When survival itself hangs in the balance, the proximity fuse reminds us that transformative military advantages demand more than technical brilliance. They require overcoming bureaucracy, skepticism, and fear of the unknown. Delaying innovation costs lives. Yet when finally unleashed, such breakthroughs can alter the very course of history. The legacy of the proximity fuse extends far beyond World War II. Every modern anti-aircraft missile employs proximity fusing as a core feature. The Patriot missiles that intercepted Scud attacks during the Gulf War used technology directly descended from the wartime Mark 32 fuse. Naval close-in weapon systems like the Phalanx, which protect ships from incoming missiles, rely on proximity fusing. Air-to-air missiles carried by fighter jets across the globe use the same principle. What began as a desperate wartime invention became the foundation of modern air defense. The scientists who built the proximity fuse went on to shape American science for decades. James Van Allen would later discover the radiation belts that bear his name. Many members of Section T became key figures in the U.S. space program. The Applied Physics Laboratory at Johns Hopkins, founded for the Proximity Fuse Project, remains a cornerstone of defense research today. The model of collaboration between universities, industry, and government established by the Fuse program became the blueprint for American technological progress throughout the Cold War. Most importantly, the proximity fuse saved untold lives. Naval historians estimate that without it, American losses in the Pacific would have been 30 to 50% higher. The kamikaze threat might have forced cancellation of the Okinawa invasion, and the planned invasion of Japan in late 1945 could have faced catastrophic casualties. In Europe, the Battle of the Bulge might have split Allied armies without proximity-fused artillery support. London could have been evacuated under unrelenting V-1 attacks. The war might have dragged into 1946 or beyond, with millions more dead. The proximity fuse stands as evidence that history's greatest victories arise not only from valor, though courage remains vital, but from the fusion of science and industry. 22 million tiny radars, each no larger than an ice cream cone, helped win the largest war in human history. They did so by solving a problem once thought unsolvable, turning the vast empty sky into a lethal barrier for enemy aircraft, and giving Allied forces the edge precisely when they needed it most.